Dear aspirant, in this module, we are going to see infrared spectrophotometry. Infrared spectrophotometry is one of the most widely used, widely adopted spectrophotometric method in the analytical laboratory to identify various chemical compounds. We will see the details of infrared spectrophotometry, its applications, etc. in the upcoming slides. The major application of infrared spectroscopy is to identify the molecule structure or the functional groups present in the particular compound. And also the spectra obtained from the analysis will be compared with the standard spectra of the particular molecule so that you can identify the compound. When it comes to the identification of the molecular structure, each molecule has its own molecular structure and bonding with each element or atom. The infrared spectroscopy utilizes the concept that molecules tend to absorb specific frequencies of light that are characteristic of corresponding structure of the molecules. The various functional groups in the chemical compounds like alcohol or carboxyl group or carbonyl group, phenyl group, alkyl group, alkene group, etc. can be identified through this particular infrared spectroscopic method. Each functional group bond is vibrating its own path like stretching or bending as per the principles we have seen in the spectrophotometric method of analysis. When the infrared light source is applied to the molecule will absorb the specific frequency of light and the frequency will be identified through the infrared analysis. Going back to the principles of infrared spectroscopy, as we have seen in the fundamentals and principles of spectroscopy in the earlier module, infrared spectroscopy deals with the infrared region of the electromagnetic spectrum, that is, light having a longer wavelength and a lower frequency than the visible light. The infrared portion of the electromagnetic spectrum is usually divided into three regions, that is near IR, that is region of 14,000 to 4,000 centimeters in US. It can excite overtone or combination modes of molecular vibration in this region. Then it is the second one is mid infrared, approximately 4,000 to 400 centimeter in US, is generally used to study the fundamental vibrations and associated rotational vibrational structures. The far infrared, approximately 400 to 10 centimeter in US, has low energy and may be used for rotational spectroscopy and low frequency vibrations. So near IR, the wavelength will be from 14,000 to 4,000 centimeter in US, mid 4,000 to 400, and far is less than 400 up to 10 centimeter in US. And each region adopts different kind of molecular excitations, including molecular vibrations and the low frequency vibrations. In infrared spectroscopy, we have seen two different units. One is wave number and another one is wavelength. Typical units of wave number used in IR spectra are reciprocal of centimeter, that is centimeter inverse. And in case of wavelength, it is denoted as micrometer. And in laboratory setup, the commonly available infrared spectroscopy instruments are Fourier transform infrared spectrophotometer and attenuated total reflection spectrophotometer. We will see more information about these two instruments in the coming slides. The classification of infrared spectroscopy region is schematically presented here Then near infrared region, which is coming around here from 12,500 to 4,000 centimeter universe wave number. And this 12,500 here marginally given in this particular scale, but what we have seen actually will be from the 40,000 to 4,000 centimeter universe. And then the mid infrared region, which is coming in the scale of 4,000 to 400 centimeter universe of wave number. And the far infrared region is coming between the 400 centimeter universe to 10 centimeter universe of wave number. Now we are going to see the various components of a infrared spectrophotometer. Like any other spectrophotometer, we can see the light source and detector and a recorder in this infrared spectrophotometer as well. So the light source generally called as a glober, which is employing a thermal light source. So the glober is containing a silicon carbide rod with a diameter of 5 to 10 millimeter and a length of 20 to 50 millimeter, and it will be electronically heated to 1000 to 1650 degrees centigrade to generate the light. And when it is coming to the process, a beam of infrared light is produced and passed through an interferometer and then split into two separate beams. This one of the beam out of two is passed through the sample and the other is passed through the reference. The beams are both reflected back towards a detector. However, first they pass through a splitter which quickly alternates which the both beams enter the detector. The two signals are then compared and a printout is obtained. So this is a general process what happens in a infrared spectrophotometer, and eventually the two beams from the reference as well as the samples will be recorded in a detector or will be captured by a detector, and this two beam setup gives an accurate spectra even if the intensity of the light source drifts over time. So the detector will capture both the beams for the test or the sample and as well as the reference and give the comparative spectra. Then it is coming to the recorder. Recorder is generally supported by a software and a computer system which is recording the signal transmitted through the detector. In this particular slide, we are seeing the schematic presentation of how the IR spectrophotometer functions with different parts. So here is the infrared source, the light, infrared light generate in this area and it is passed through the splitter, and it will be separated to two beams here. One beam passed through the reference and another beam passed through the sample, and through the again through the splitter it will both the beams will be detected and it will be the readings are recorded here in the system. And the spectra generally looks like this. So here you will get the spectra for the reference as well as spectra for the sample, and both will be compared and confirmed if both are matching together. And also you can read about the functional group based on the peaks identified in the spectra. In this particular slide, we are seeing the image of a typical infrared spectrophotometer, which is a widely used one that is called Fourier transform infrared spectrophotometer, which collects high resolution spectral data over a wide spectral range. In this particular spectrophotometer, we use the potassium bromide for the sample preparation. In this particular slide, we are seeing attenuated total reflection infrared spectrophotometer, ATR infrared spectrophotometer. Alternated total reflection is a sampling technique used in conjunction with infrared spectroscopy, which enables samples to be examined directly in the solid or liquid state without further preparation. So basically, this particular instrument enable you to use the samples directly, either it is a solid or liquid. So we need not to go for any sample preparation like potassium bromide pellets or something which is generally used in the Fourier transform infrared spectrophotometer. So this is something advanced than the Fourier transform IR spectrophotometer, and we can use the sample directly and easily. That is the most advantage of the particular ATR IR spectrophotometer. Now we are seeing some of the sample preparation techniques employed in infrared spectroscopy analysis. The samples are prepared using different mulling agents which has an oily texture. So basically a thin layer of mull can now applied and a salt plate will be used for the measurement. In most of the cases in Fourier transform infrared spectroscopy, potassium bromide will be used as a mulling agent and a thin pellet will be formed for the analysis. Liquid samples are generally kept between two salt plates and measured since the plates are transparent to IR light. The plates are made up of sodium chloride, calcium fluoride or potassium bromide. Solvents for liquid samples like carbon tetrachloride, carbon disulfide can be used for the infrared spectroscopy measurements. Solvents for polar materials which can include chloroform, methylene chloride, acetonitrile and acetone. And in case of attenuated IR spectroscopy, you can use the sample directly to analyze the IR spectrum. Once you have started to use the infrared spectrophotometer, once you do the analysis, how you are going to interpret infrared spectra obtained from the analysis. If the drug you are going to analyze, which is official in pharmacopoeia, then the pharmacopoeia itself there will be a reference spectra available, which we can compare with the sample spectra what we got from the test. So both spectra will be compared and confirmed the given compound, the test compound is the same compound which is official in the pharmacopoeia, so that you can confirm the compound. In case the pharmacopoeia doesn't give any reference spectra or the drug is not official in the pharmacopoeia, then you can go through the certificate of analysis of the particular compound. The certificate of analysis can provide a spectra which can be compared with the spectra obtained from the test sample and can be confirmed. If the spectra is neither available in pharmacopoeia nor in COA, certificate of analysis of the standard, then you can analyze both standard, the reference standard as well as the test sample and compare the spectra obtained from the standard along with the test sample. Both spectra can be compared and confirmed that the compound is same as the standard. So this is how qualitatively you can identify the compound or confirm the compound using the IR spectrum. And the same spectra what you obtained from the reference standard can be saved in the software for future identification or analysis of the samples. So how will you interpret a IR spectra of unknown sample? You have got a unknown sample to analyze, and how you are going to interpret the spectra obtained from unknown sample. The IR spectra of the unknown samples can be used for the structural elucidation. So if you have a new drug or new identified compound which has to be elucidated for the structure, then you can use the IR spectra for the structure of the particular compound. The functional groups of the compound can be identified by analyzing through the IR spectrophotometry. When a new synthesis reaction has taken place during a research, the required functional group formation and the reaction completion can be confirmed or ensured by the infrared analysis of the product obtained from the new synthesis. So once the new synthesis is your objective of the new synthesis is particular compound, and the particular compound whether it is formed or not can be confirmed by the infrared spectroscopy analysis qualitatively. Now we are going to see how will you identify the functional groups from a spectra obtained from infrared spectroscopy. So in this scale you can see from 4000 to 3000 centimeter universe wave numbers, you can see heteroatoms X H bonds and CH bonds, and also you can see NH bond, OH bond, CONH bond in this particular region 4000 to 3000, and 3000 to 2000 you can see C triple bond C, C triple bond N, N double bond C double bond O, N double bond C double bond S, N double bond C double bond N. These kind of functional groups can be identified in this particular region of 2300 to 2100. And in case of 1800 to 1500, you can see C double bond N and C double bond C. And halogenated compounds generally obtained in the region of around 1300 to 700 centimeter universe. And organometallic compounds, as the wave number is getting lower, you can find only the organometallic compounds. Here you can see another representation of how will you identify the functional groups using a infrared spectroscopy. It is based on the percentage transmission obtained from the spectra and the wave number region in the x-axis here. And in case of 4000 to 3000 centimeter universe of wavelength, you can see NH stretch and OH stretch. And from 3500 to 3000, you can see alkyne CH stretch, alkenyl CH stretch. Also around 2850 to 3100, you can see CH stretch. And you can see in between 2500 to 2000 or approximately around 2100 to 2260 centimeter universe, C triple bond N as well as C triple bond C. And around 1650 to 1800 centimeter universe, you can see the C double bond O stretch. And also in the region of lower wave numbers less than 1000, this is generally called as fingerprint region, you can see only the organometallic compounds, and you can see that here the ortho meta para substitution patterns of aromations. In continuation to functional group identification by using infrared spectroscopy, from the spectra you can see the functional groups or the functional class of sulfur as well as the phosphorus from characteristic absorption given in this particular table. In case of functional class of sulfur, you have SH thiols, SOR esters, SS disulfides and S double bond S thiocarbonyl groups, which specifically fall in this particular mentioned characteristic absorptions, or you can say that the wave number region. S double bond O also falls in this specified characteristic wave number region. And in case of phosphorus functions, phosphine, phosphoric acid, POR esters, and P double bond O phosphine groups are falling in the specific wave number region from the can be identified from the spectra. Similarly, for silicon functions, we can have a characteristic absorption of this particular wave number region that includes silane groups, silicon OR groups, silicon CH3 groups. And in case of oxidized nitrogen function, that includes NOH oxime groups, NO amine groups, N double bond O nitroso nitrogen groups. All these functional groups can be identified through this specific characteristic absorption in this particular wave number region. In addition to the several applications what we have already seen for the IR spectroscopy, like identification of the compounds, structural elucidation of the compounds, etc., IR spectroscopy also used to analyze the crystalline quality of the bulk drug in pharmaceutical formulations. And it is also used to evaluate the pharmaceutical properties of tablets by inline NIR monitoring during the granulation process. So this is a continuous process, online process. When the granulation process happens, immediately the IR spectroscopy done to confirm the pharmaceutical properties of the tablets. And also it is used to evaluate the pharmaceutical properties of the tablets in which the drug substance undergoes crystal polymorphic transformation during the granulation process by inline NIR monitoring. So it is similar to the second point, but here we are specifically seeing the change in the polymorphic nature of the drug substance during the granulation process. And the prediction of dissolution properties of tablets or other solid dosage forms can be used by a near infrared spectra, that is NIR spectra of the compressed tablets. The tablet quality evaluation during the tablet manufacturing process based on the physical and chemical information in the near IR spectra of the compressed tablets. This is also one of the application of infrared spectroscopy during the pharmaceutical manufacturing process. Evaluation of polymorphic content of bilayer tablets also being done using the NIR spectra. And sometimes it is used to monitor the tablet coating process of the control release formulations. And the NIR spectrophotometers are generally is handheld so that it is very effective, useful in the pharmaceutical industry. Now it comes to the calibration of infrared spectrophotometer. Generally, this infrared spectrophotometer are calibrated for the wave number regions. So a polystyrene film is used for the calibration of infrared spectrophotometer. The spectrum of polystyrene film will be scanned from the range of 4000 to 450 centimeter universe, and the obtained wave number will be compared as follows. That means the wave number specifically already established for the polystyrene film is already available, and what obtained should be within this minimum and maximum tolerance limit. So you will have a spectra which is having the wave numbers mentioned in the spectra, which is already established, and you should get, whenever you do the calibration, you should get the wave number within this particular minimum and maximum tolerance wave number limits. If it is false in these limits, then your calibration is passed and your machine is giving proper or appropriate or real results of the particular sample. So aspirants, in this module we have seen the various aspects of infrared spectrophotometry, including the applications, instrumentation, sample preparation, and how to interpret infrared spectra and other pharmaceutical applications. In the next module, we are going to see the another spectrophotometric method called atomic absorption spectrophotometry. Thank you.